Alright, so up until this point we've been talking about primarily lines, parameterized lines and curves in 2 or 3 dimensions. Kind of the natural progression is to now look at surfaces. And we kind of covered a little bit about surfaces and directional derivatives the past couple videos, and so I thought now would be a good time to start talking about surface integrals themselves. And so the first and most basic kind of surface integral is actually just finding the surface area. By comparison, you'll remember in Calc 2 learning how to calculate arc length, right? We learned how to calculate length of a curve. Well, now in Calc 3 we started talking about, what's the flux through a curve, what's the circulation of a curve. And so the first step to figuring out the flux of a surface or other things similar to that is going to be to define what the surface is in the first place. So in other words, we can't calculate flux along a line until we've defined arc length. Therefore, we also can't define flux through a surface until we define the surface. And so I've got this arbitrary surface here, and because we're in Cartesian coordinates, and mind you, there are other techniques that have similar ideas that work with spherical and cylindrical coordinates. As a matter of fact, the gradient becomes a lot more complicated in spherical and cylindrical coordinates. So we're kind of learning the Cartesian way first because it fosters an understanding. So I've got this arbitrary curve, and I'm going to pick a surface element. Kind of like with arc length, we picked a little ds, right? Well, now we're going to pick a little ds, but the s is a big S now. So for a segment, we use a little s. For a surface, we use a big S. You may want to accentuate the size of the S just to make sure that you know that it is a surface element. Now, some people will also call this dA, which I occasionally use. What I've kind of restricted myself to using now is I'll use dA for a flat surface, and I'll use ds for a curved surface. So I've been using ds for a while now for this application. So on a curved surface, I'm going to call a surface element ds, and we're going to go ahead and zoom in on this surface element. You'll notice first that I have a shadow region. I've got a shadow region boxed out. And what I mean by a shadow region is if we looked down from the z-axis onto this curved shape, we would actually just see a rectangle. And that rectangle would be bounded by this xy plane shape. And so the curve does exist in the z direction, but if we didn't have a z direction, we would just be this rectangle or square, whatever it might be, and it's going to have boundaries. So in other words, x is going to go from 0 to some number, y will go from 0 to some number, just like bounds in any sort of integration. Now we just have two sets of boundaries, now that we're in a three-dimensional space. So the first thing I want you to notice about this element here is that it has rates of change in different directions. And so, for example, if this is in the y direction, right, this is in the y direction, we're going to call this little part of the element, we're going to call it dy. And because this likewise is in the x direction, I'm going to call this dx. And truly, the slope of this curve is going to be the change in z with respect, I called this dz, this is dx. The slope of this curve would be dz dx. So how much does z grow for x's growth? So likewise, we'll call this height here dz, and also this height dz. So in other words, what we're looking at here is as x changes by a little bit on the surface, how much does z change? As y changes a little bit on the surface, how much does z change? And what you'll find is that you can write two vectors. I'm going to call this one over here v, and I'll call this one u. And if we use our vector notation, let's say u, how much does it go in the x direction? Well, it goes a small amount in the x direction. So dx in the x direction. It's 90 degrees to the y, so therefore it has no y component. And then it grows vertically a small amount dz. And then for v, we have no growth in the x direction, it's all in the y direction. We have a small bit of growth in the y direction, and for that growth in the y direction, we have a small growth in the z direction. So now we have two vectors. And this is why cross products, one of the reasons why cross products are so important for vectors, is we can actually, just like I proved earlier on in this series, the cross product of two vectors represents the area of the parallelogram of which they are on the outside of. So in other words, we can find the area of this little element ds by taking the cross product of u and v, and then taking the magnitude of those. So we want to figure out what u cross v is, and we'll set up our determinant matrix, and dx, 0 dz, 0 dy, dz. And we'll go ahead and take the cross product. For the I component, it's 0 times, okay, anything times 0 is 0, minus dy times dz. So we've got minus dy dz in the x component. For the y component, j, we have dz times 0, which is 0, minus dx times dz. So we have minus dx dz for the y component, and then for the k component in the z direction, we have dx times dy minus 0. So that's dx dy. So this right here is u cross v. This is u cross v. And what it represents is a vector pointing normal to ds. Remember, the cross product always points normal. So I'll draw a vector coming out of the surface. It's going to be 90 degrees to both v and u. So it's pointing normal to the surface, and that's our vector u cross v. And it has a length that is equal to the surface area of the element. So if we want to figure out the surface area here, what we would do is we would take the absolute, or the magnitude of this vector. And so to do that, I'm going to make a little bit of space up here. So for the magnitude, we're just going to use the concept of Pythagorean's theorem. And so what we'll do is we'll say the magnitude of u cross v is equal to the square root of x squared, which that component is dy dz squared, plus the y component dx dz squared, plus this component here, which is dx dy squared. And so this is the area of this little surface element. And so now what we're going to do is just kind of simplify it a little bit. So you'll notice that when we square this, we get dy squared dz squared plus dx squared dz squared. And of course, because we squared them, they're all now positive. Okay, now the next trick we've got up our sleeves is we're going to pull a dx squared and a dy squared out of everything. So under the radical, we're going to pull out a dx squared and a dy squared and factor it out of everything. Well, if we pull out a dy squared, then this is going to go away, and what we'll end up with here is dz squared over dx squared. And feel free to pause it and prove that to yourself, because the dx squareds cancel and you're left with dy squared dz squared. And then over on this one, if we pull out a dx squared and a dy squared, what we end up with is dz squared over dy squared. And then of course we pulled out a dx squared and a dy squared, so this is now 1. Alright, so now that we're at this point, we're going to head use the rules of taking square roots and just take the square root of dx squared dy squared and leave this other stuff down in the radical and simplify it. So I have dz squared. I'm going to write it as dz over dx squared, because I can write dz squared over dx squared as dz dx squared. And then I'll do it for this next component, which is dz dy squared plus 1, and then the root ends there. And now we have a dx dy outside of the root. Alright, so we just solved for our small surface element. And it turns out that to find the surface area in Cartesian coordinates for a surface like this, what we will do is to find the total surface area, because ds equals this, if we take the integral of both sides, what you'll find is that s equals the double integral of this thing right here with respect to dx and dy. So if y went from 0 to y, then we would put 0 to y here, x goes from 0 to x. You always want to make sure that your innermost values dx matches with x, and then as you go to dy, it's another step. So you want to make sure these are in the correct order to match your boundaries. But ultimately, this is how we find surface area. And then in a later video, we'll start talking, because remember that ds itself, ds, the vector, u cross v, not just the area, but that's normal to the surface. So we're going to be able to use that vector to figure out flux through a surface. I hope this was helpful, and I'll see you next video.